Hey guys, this week we're going to talk about Chapter 10, Section 2 and Chapter 10, Section 3, Taylor series and finding and using Taylor series. So last week we talked about Taylor polynomials, and basically what we said is that some functions are better to work with if they have a polynomial representation. And so we approximated functions using different degree polynomials. And so we called these polynomials Taylor polynomials that approximated the function for x near a, which is also called the center. Now, what we're going to look at now is Taylor series. So Taylor series are not approximations. These are going to actually equal the function values for specific inputs. So let's get into it. All right, so here it is, Taylor series for a function f of x about x equals a. So again, a we call the center. So if your function can be represented by a power series about the center a, then f of x, your function, is equal. It's not approximately, it's actually equal to the sum of its Taylor series. Now look at what the definition of a Taylor series is. Doesn't it look exactly like the Taylor polynomials that we worked with? Well, there's one subtle difference, and the difference is these three dots at the end. So a Taylor series, let's write the difference here. Taylor polynomials are finite. A Taylor series is infinite. All right, so last time we looked at polynomials, we looked at degree 3, degree 4, degree n polynomials, all of which were finite. But here with a Taylor series, that series is infinite. It's never going to end. And we're going to see that some functions' Taylor series converge for all inputs, for all values of x, whereas some Taylor series converge for only certain values of x. So let's first talk about where this came from. So I did promise this last lecture. I gave you guys the formula, but I didn't really talk about where it came from. So I want to give you some intuition of where this Taylor series comes from. And again, this is the same thing that we learned last week, except the subtle ... means it's infinite. So let's talk about where this comes from. So if f of x can be represented as a power series, remember we talked about what power series looked like the week before last. Well, if a function can be represented as a power series, it's going to look exactly like this, where a is the center of our power series, and a sub n is for each n is going to be a coefficient. Now, all we need to do is figure out what these coefficients are, and that's going to tell us what our Taylor series is going to look like. And so the basic idea here is if we know that our function can be represented like this, okay, so that's just the definition of a power series. Well, what happens if I plug in my center in for each x? What's going to happen? Well, let's see. I have a sub 0 plus a sub 1 times x. If I plug in a for x, I get a minus a here, plus a sub 2, a minus a again, plus ... a sub n, a minus a to the n, and it keeps going in this pattern. And now you should see that, well, a minus a is 0, so this clears, this clears, this clears, they all clear, except for this guy right here. So what we can say something about our very first number, our very first coefficient here, and that is that f of a, let's write it like this. Therefore, a naught is going to equal f of a, which we can find really easily because a is going to be some number, whatever the center is. So we just take that number and stick it into our function. All right. So that's that. Let's box this. Now, what about the other coefficients? What about a sub 1, a sub 2, a sub n? And, you know, maybe I should continue this a little bit. Let's actually continue it to a sub 4, just so you guys can spot the pattern. So we have x minus a to the 3 plus a sub 4, x minus a to the 4 plus a sub n, x minus a to the n plus dot dot dot. Okay, so what I'm going to do now is I'm going to take the derivative of f of x, because again, the goal is to see what these coefficients are. A sub 0, a sub 1, etc., etc. So if I take the first derivative of my function f of x, well, this is a constant, so that goes to 0. Now, a sub 1 times x minus a, what's the derivative of that? Keep the first, product rule, keep the first times the derivative of the second. What's the derivative of x minus a constant? It's just 1, right? Keep the first times the derivative of the second, plus, now you keep the second times the derivative of the first. Well, derivative of a constant is 0, so that goes to simply a sub 1 times 1, which is just a sub 1. All right? So we have 0 plus a sub 1. The derivative of this guy right here is going to be 2a sub 2, x minus a to the first. The derivative of the third one is 3a sub 3, x minus a squared. The fourth one is 4a sub 4, x minus a to the third. And finally, the nth one is n times a sub n, x minus a, n minus 1. So I'm just taking derivatives term by term, right? We know how to take derivatives. These a sub n's are constants. The a is a constant, it's just whatever our center is. And so we just apply our elementary derivative calculations here. Now, what happens when I plug in a into my derivative? Well, look, if I plug in a for x, anywhere I see an x, all of these are going to go to 0 again, right? All of those are going to go to 0. And so what I end up having, right? I have a sub 1 plus a bunch of zeros, so that's just a sub 1. So this is going to be a sub 1, and I'll box that. All right, so I have my second coefficient figured out, right? So I'm trying to figure out what the Taylor series is, and to do that, I need to know what my coefficients a sub 0, a sub 1, a sub 2 are. And so far, I have a sub 0 and a sub 1. Now let's figure out what a sub 2 is, and see if you can spot a pattern. Well, if I take the second derivative, so I'm taking the derivative of the first derivative, the constant goes to 0. Then I have 2a sub 2. Yeah, and that's it for that one. The second one I have, and I'm going to write it like this. Instead of 6 using the power rule, I'm going to write 3 times 2x minus a, right? Excuse me. So that's that. Let's see. Just want to make sure. There we go. Okay, good. All right, so we took care of that one. Going on to the next term right here, I have 4 times 3, x minus a squared. So that's the derivative of that guy. And finally, plus dot dot dot, I have n times n minus 1, x minus a to the n minus 2. Just using the power rule, taking the derivative of this guy. So that is that. Now, if I plug in, again, I'm doing the same old thing here. If I plug in a into the second derivative, what's going to happen is this is going to go away. This is going to go away. All of that's going to go away. The only thing that stays is 2a sub 2. So that is my, I'm going to have my coefficient a sub 2 is f double prime of a over 2. And we're going to get to that in a minute. But I just want to highlight this point here so that we can recognize a pattern. All right, let's take the third derivative. So f3 of x. I'm just taking the derivative of this guy, term by term. So the derivative of this goes to 0. The derivative of this is just 3 times 2, right? And actually, I think I forgot my a's. That's not good. So this should have an a sub 3 right here. This should have an a sub 4 up here. I apologize about that. This should have an a sub n right here. Okay. So I have, when I take the derivative of this thing, I just have a sub 3 times 2. And then when I take the derivative of this guy, I have a sub 4 times 3 times 2 times x minus a plus plus a sub n times n minus 1 times n minus 2 times x minus a to the n minus 3. Okay, so what happens when I plug in a into my third derivative? Well, this goes away and everything else goes away, right? When I plug a in for x. So what I'm left with when I do that is just a sub 3 times 2. Now let's do one more and then we can generalize. So let's take the fourth derivative. The fourth derivative. So I'm just looking at this guy and I'm taking the derivative of each term by term. So this goes to 0 because it's a constant. This is simply a sub 4 times 3 times 2 plus a sub n times n minus 1 times n minus 2 times n minus 3 times x minus a to the n minus 4. So that is our fourth derivative. And what happens if we plug in a into our fourth derivative? Well, this is all going to go to 0, right? Because if I plug in a in for x, 0 times all of this stuff is just going to be 0. And I'm just left with a sub 4 times 3 times 2. Now let's look at the pattern here, all right? Notice that I can isolate all of my coefficients, my a sub whatevers, right? If I isolate the first one, well, these are already isolated. The coefficients a naught and a sub 1 are isolated. If I look at this guy, well, this guy, if I divide both sides by 2, I get a sub 2 is equal to f double prime of a divided by 2. And if I isolate this one, a sub 3 is going to equal the third derivative, plug in a, divided by 3 times 2. And isn't 2 just 2 factorial? And isn't 3 times 2 just 3 factorial? Right? And what about over here? If I isolate a sub 4, I get a sub 4 is equal to f fourth derivative of a divided by 4 times 3 times 2, which is equal to, you guessed it, 4 factorial. So let's generalize this. What is a sub n going to be? What is my nth coefficient going to be? Well, it's going to be our nth derivative, plug in a, divided by, well, n factorial. That's the pattern that we're recognizing here. So this is how this Taylor series comes about. It says, hey, every coefficient is going to have this form. And that's what you see right here. We see f of a, f prime of a, f double prime of a over 2 factorial, etc. So these are all my coefficients. And so hopefully this made some sense about, how this Taylor series came to be. So all the coefficients are going to be of this form, and Taylor series are derived from power series, functions that can be represented as a power series. So let's move forward here. And this isn't anything new. It says find the first 4 non-zero terms of the Taylor series for the function f of x equals 6 over x about 2. So this is our A. When they say about, that means that's our center. And so what we want to do is we want to do the same thing that we did with the Taylor polynomials, because essentially what we're trying to do when it says find the first 4 non-zero terms is we're looking for the Taylor polynomial. We're just cutting off the Taylor series to approximate this function instead of giving the exact value of it, right? Okay, so let's go ahead and do that. So we're going to do just like we did last time with the Taylor polynomials. First we have f of x, and that's 6 over x, which I'm going to write as 6 to the negative 1 to make it easier to take derivatives. I want to find the first 4 terms, so I'm now going to do f prime of x. That's going to be our second term when we plug R2 in, and attach, the rest of the terms for the Taylor series. So f prime of x, if I take the derivative of 6x to the minus 1, I get negative 6x to the negative 2. Second derivative, well, that's going to be 12x to the negative 3. The third derivative is equal to, well, that's going to be negative 36x to the negative 4. So there I go. I have 4 terms, so let's go ahead and stop there. Now what I want to do is I want to plug my center into each of these functions. First of all, f of 2 is going to be 6 times 2 to the negative 1, which is equal to 3. All right, so this is the point where I'm finding my, I'm finding part of my coefficient. I still have to deal with the factorial here, but let's go ahead and plug in 2 into our first derivative function. We have negative 6, 2 to the negative 2, and that is going to give me negative 3 over 2. All right, let's do the second derivative at 2. We get 12 times 2 to the negative 3, and that is going to give me 3 over 2. And finally, if I plug in 2 into our third derivative, we get negative 36, 2 to the negative 4, and that is going to give us negative 9 over 4. All right, so we got to use this in our Taylor series. So what we have here is we have 6 over x is approximately because we're not going to do the dot, dot, dot. We're just cutting it off for the first 4 terms. So it's going to be approximately f of a, so f of 2 is 3, plus f prime of a, that's negative 3 over 2, times x minus 2, plus 3 over 2 factorial, times x minus 2 squared, minus 9 over 4 over 3 factorial, times x minus 2 to the third. So here, this is our answer. This is our first 4 terms. 1, 2, 3, and 4. All right, so that is our Taylor polynomial that represents an approximation for the function 6 over x. Okay, so these are going to be some important Taylor series that we're going to talk about over and over again in this lecture. The first one is e to the x. And I want to say that we looked at all 3 of these in the last lecture. But, you should, if you're interested, you should derive these for yourself just based on the derivative function. But I think we did look at this last time. I think the only one that we may not have looked at was sine, but we definitely did e to the x and cosine of x. Now, I want to ask you something. What do I want to ask you? Okay, so look at what this says here. E to the x equals, not just approximate, equals 1 plus x squared over 2 factorial plus blah, 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 blah. all the way till forever. This thing actually equals this. There is no approximation here. And so what that means is that this function e to the x is the exact same thing as the right side of this equation, this Taylor series expansion. And it turns out that some functions are equal to their Taylor series for all values of x, right? Some functions are not. We're going to look at both cases here. But it turns out that e to the x actually is equal to its Taylor series for every value of x. It converges to its Taylor series for every single value of x. So let's go ahead and actually prove that, because I think it's important. So what are we going to show? We want to show that e to the x is equal to its Taylor series for every value of x. Okay, so what do we know? Well, we have the following. We have e to the x is equal to 1 plus x squared over 2 factorial plus x to the 3 over 3 factorial plus x to the 4 over 4 factorial plus ... forever and ever. Now, what I want to do, here's the strategy. I want to use the ratio test to see where this series converges to. If the series diverges for any value of x, then we cannot say that the series equals e to the x for those x's, okay? So I want to see where does this converge? That's what I want to know. Where does this converge? So to do that, I need to use the ratio test. But before I use the ratio test, I need to actually write this thing in terms of n, right? You guys remember the ratio test? The ratio test was the following. The limit, we took the limit as n went to infinity of a sub n plus 1 over a sub n. Okay? Now the question is, how can we write each of these terms? That's what our a sub n is. How can we write that? Well, I can do the following. I can say that this guy is going to equal the sum as n equals 0 to infinity of x to the n over n factorial. See if that makes sense to you. When we plug in n equals 0, we get x to the 0 over 0 factorial. That does indeed equal 1. When we plug in n equals 1, we get x to the first over 1 factorial. Well, that's x. Yes, we got the next term. Plus, when n equals 2, x squared over 2 factorial. Yes, okay, so this is the formula that represents the above series. Now, so what we have here is we have a sub n is equal to x to the n over n factorial. And a sub n plus 1, well, we're simply substituting an n plus 1 in for n. So we get x to the n plus 1 over n plus 1 factorial. And now we can just plug this stuff into our absolute value bars. So we have the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial divided by a sub n, x to the n over n factorial. All right, let's clean this up a little bit because this is a hot mess right now. Let's do complex division, which means multiplying by the reciprocal. We have x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Well, let's clean this up. We've done a lot of examples with the ratio test, so I'm not going to go in depth with how we did this stuff, but you know, if you forgot, you should look at the ratio test video. I think that was the video called Power Series and Interval of Convergence. So if you're a little shaky on that, check that video out again. So here's what we do. So x to the n plus 1 divided by x to the n, well, we can subtract the exponents. N plus 1 minus n is just going to give me x to the first. So we have the limit as n goes to infinity of x, and then n factorial over n plus 1 factorial. We've done lots of examples like this. This is just going to be x over n plus 1. All right, so that's what that is simplified. Now, remember with the x, I need to leave it in the absolute value of bars, but I can take the n terms out because n is always going to be positive, right? N starts at 0. So we have the limit. We have this absolute value of x. The limit as n goes to infinity of 1 over n plus 1. So what happens to this? This whole thing goes to 0, right? So we just have the absolute value of x times 0 equals 0. So for which values of x is this going to equal 0 for? Well, it's going to equal 0 for all values of x. And remember what the ratio test said. It said, you know, if this limit that we get is less than 1, then it converges, right? So for all x, this thing is going to converge, right? Because it's always going to be 0. 0 is less than 1. So therefore, what we can conclude is that the series converges for all x. That's pretty cool. E to the x is represented by this series. The series converges for all x. So we can use any value of x here. Some of the series that we're going to look at, we can't. We have to omit some x values, and because those x values aren't going to give us a valid Taylor series expansion. But for e to the x, it's going to work for any value of x. Okay, let's take a look at this example here. So we want to recognize this series as a Taylor series that we know. And we want to recognize it, evaluate it at a particular value of x, and then it says find the sum of this convergent series. All right, so we're going to assume that the series converges for a specific value of x because they tell us that it does. So our job right now is to recognize which one of these series. Oh, I guess I don't. Where is it? Is it here? Sorry. Which of these three series most resemble the one that we have? Well, what you should notice is the factorials, right? We have 2 factorial over 4 factorial, 6 factorial, etc. And this looks very closely like cosine of x. So we have cosine of x. The Taylor series for that is 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial plus dot, dot, dot. So that looks very similar to what we have here. The only substitutions is the x, right? So what we can do is we can really just set one of these equal to the corresponding number in the same spot and solve for x and see if it works for the other ones. So like x squared is equal to 4. So if I take the square root of both sides, x is equal to plus or minus 2. I'm just going to go with 2 here. So we have 2. Is it true that 2 squared is equal to 4? Well, yeah, it is. Is it true that 2 to the 4th is equal to 16? Well, yeah, that's true. Is it true that 2 to the 6th is equal to 64? Yeah, that's true. So our x value is 2. Our x value is 2. So what we can do, since our x value is 2, we can just sub it in here. For cosine x is cosine 2 equals 1 minus 2 squared over 2 factorial plus 2 to the 4 over 4 factorial minus 2 to the 6 over 6 factorial. And they tell us that this thing is going to converge to the cosine of 2, right? Whatever our x value is. So all we have to do is evaluate this in the calculator. And this is giving me negative 0.42. Okay, so that is going to be our answer here. So that is what the series converges to at x equals 2. What about this one? So which of the three series, e to the x, sine of x, or cosine of x, does this look like? Well, I'm thinking that this looks most like e to the x. And the reason that I'm thinking that is because, well, for the first thing I notice is that there's all plus signs here. Whereas with sine of x and cosine of x, the Taylor series alternates signs, but the e to the x series does not. So what we have is we have that e to the x is equal to 1 plus x squared over 2 factorial plus, sorry guys, I'm not writing very well tonight, 64 over 3 factorial plus 256 over 4 factorial, and so forth and so forth. So in order to match this up to what we have, what does x have to be? Well, it's pretty clear that 4 is in the position of x, so x should be 4. And we could check that. Is 4 squared 16? Yep. Is, well, this, I don't know why I wrote it like this. Sorry. Kind of losing it. Let's see. Yeah, so this is going to be x to the 3. Sorry, guys. Technical difficulties here. Is it true that 4 to the 3rd power is 64? Well, yeah, that's true. Is it true that 4 to the 4th power is 256? Yes, that's true. So x is equal to 4, and therefore we have e to the 4th power is equal to 1 plus 4 plus, again, I'm just plugging in 4 in for x into this Taylor series. And they do tell us it's convergent when x equals 4. So let's compute this. Well, remember, we're just trying to figure out what the sum is. Well, the sum is e to the 4th, right? The left and the right-hand side are equal, so this whole infinite sum is equal to e to the 4th. Now, what is e to the 4th in decimal form? Well, e to the 4th is approximately 54.6. So that is going to be our answer here. Okay, so we talked about e to the x, sine of x, and cosine of x in terms of their Taylor series. Let's talk about Taylor series for functions of this form. F of x equals 1 plus x to the p, where p can be any number. Okay, and let's talk about, in particular, them being centered at 0. So let's kind of try to derive the formula here. Remember what we do when we find the Taylor series. We start with f of x, and then we start taking derivatives. So here's this. Here's f of x. Now what is f prime of x going to be? Well, I got to use the chain rule, so I multiply the p on the outside, 1 plus x to the p minus 1 times the derivative of the inside, which is simply 1. So we don't have to keep doing that every time. All right? The second derivative of this function is going to be, well, p times p minus 1, 1 plus x raised to the p minus 2. I'm just taking 1 away from the power. This is just simple application of the power rule. And the chain rule, we really don't have to do any work because we're just multiplying by the derivative of 1 plus x, which is 1. So, all right, what about the third derivative of x? Well, that's going to be p times p minus 1 times p minus 2 times 1 plus x to the p minus 3. And it continues on like this. What about, let's evaluate some of these derivatives at the center, which is 0. Well, first of all, what is f of 0 going to be? If I plug in 0 for x, I get 1 plus 0 to the p. 1 to any power is always 1, so this is going to be 1. F prime of 0. If I plug in 0 into our first derivative function, well, again, we get 1 to a power. 1 to any power is 1. 1 times p is p, so this guy is going to be p. F double prime of 0. Again, just plugging in 0 for x. 1 to any power is 1. And 1 times p minus 1, well, that's just p times p minus 1. And finally, if I plug 0 into the third derivative, I get I get p times p minus 1 times p minus 2. All right, so let's go ahead and write out our Taylor series expansion at this point. So what we have is that this guy, this function, 1 plus x to the p, can be represented with a Taylor series in the following way. We have 1 plus, again, I'm just using that formula that we've been using with, so we have f of a, which is 1, plus the coefficient of this guy right here, p, times x minus a, well, x minus 0 is just x, plus p times p minus 1 times x minus 0, x squared, over 2 factorial, plus p times p minus 1 times p minus 2 over 3 factorial, x to the third, plus dot, dot, dot. And so this is our Taylor series expansion for 1 plus x to the p, and this is valid when x is between 1 and negative 1. All right, so there is a little formula that we're going to be using alongside with the sine, cosine, and e to the x expansion. So let's do some examples with this formula. It says, find the Taylor series about x equals 0 for f of x equals 1 plus x, and explain why the result is a geometric series. Okay, so let's see. What do we have here? So we have f of x is equal to 1 over 1 plus x. Now, in order to use my binomial expansion, I want to make sure that I have 1 plus x to a power p. Well, how can I write this as 1 plus x to a power p? Well, I can simply write it as 1 plus x to the negative 1, right? So in this case, p is equal to negative 1. And so I can use that expansion. So I can use this formula right here with p being negative 1. So what I have is f of x, which equals 1 plus x to the negative 1, is going to equal, when I plug these numbers into my binomial expansion, again, p is negative 1, so just using that formula on the previous slide, I get 1 minus x minus 1 minus 1 minus 1 over 2 factorial, x squared, minus 1, negative 2, negative 3 over 3 factorial, x cubed, and so forth. So let's go ahead and simplify this. I get f of x is equal to 1 plus x to the negative 1. And let's see. Let's clean it up a little bit. So this is going to give me, when I clean this up, I'm going to get 1 minus x plus x squared. Right? This cleans up to just x squared. minus x to the 3 plus dot, dot, dot. And what we can see here is that we have a geometric series. So the first part of the question is answered. This is the Taylor series. So this is the Taylor series for the function 1 over 1 plus x. The second part of the question says, how do you know it's geometric? Well, we can see it from the pattern, right? So what's the common ratio here? What do I have to multiply each term by to get the next? Well, I got to multiply by negative x. So geometric with common ratio of negative x. All right, now let's think about this for a second. Now, I mentioned earlier that that the Taylor series representation of a function will not converge for all x. And what that means is that for those x values, we cannot represent the function with a Taylor series. Okay? So with e to the x, any x we could plug in. Any x would work with the Taylor series. We could plug in 1, we could plug in 2, we could plug in negative a million. Any x would work. But that's not always the case, and we're going to see why right now. So we know something about geometric series and when they converge and when they diverge. And what we know is that if the absolute value, so what we know about geometric series is that the absolute value of the common ratio had better be less than 1. That's the condition for convergence of a geometric series. So if we were to take the absolute value away, well, I mean, we would have two things, and I know people do this differently, but this is the way it makes sense in my head. We can either have negative x is less than 1, or we can have x is less than 1, right? Whatever's in the absolute value bar could be negative or positive. When I divide by a negative, that inequality sign flips with this guy. So that's going to flip, and then we still have x is less than 1. And so what we have here is x is between negative 1 and 1. So these are the x values for which the series equals the function. So these are all the x values that that this series converges on. So if x is between negative 1 and 1, yes, the series does converge, and it converges to this guy. If it's outside of that interval, it's not going to converge. Okay, so for instance, let's think of something outside of this interval. How about 2? X equals 2. Well, 1 plus 2 to the negative 1 is not actually going to equal this infinite series. 1 minus 2 plus 2 squared minus 2 to the 3. Remember, this is only valid. This is only equal to this series when x is between negative 1 and 1. In that, when x is within that interval of convergence. All right, excellent. So that was our first example with the binomial expansion, so that 1 plus x to the p. Let's try another one that's pretty similar in spirit. So find the Taylor series about x equals 0 for f of x equals 1 plus x. Well, this looks pretty close to 1 plus x to a power, and in fact, I can write this with a power p as 1 plus x to the 1/2, right? Same exact thing. So what I have is just using that formula right here, just using this formula, I'm plugging in 1/2 anywhere I see a p. What I'm going to end up getting is, well, let's see, I have 1 plus 1/2 x plus 1/2 times 1/2 minus 1 over 2 factorial x squared plus a half times a half minus 1 times a half minus 2 over 3 factorial x to the third plus dot dot dot. And so we can clean this up a little bit to give us 1 plus 1/2 x minus 1/8 x squared plus, oops, let's try that again. All right, so this is our Taylor series for this function square root of 1 plus x. And that's about x equals 0. Okay, let's look at this guy. So it says find the Taylor series for the function f of x equals ln of x at x equals 1 and investigate the convergence. So remember, the convergence is going to tell us which values of x I can actually plug into the Taylor series. So let's start taking derivatives. So what we have is we have f of x. So the first thing I'm trying to do is I'm trying to write my Taylor series out. Once I do that, I want to notice a pattern so that I can write a formula for it. And once I have that formula, I'm going to investigate the convergence by using the ratio test. So let's do it. So first of all, f of x is equal to ln of x. F prime of x, we all know, is our friend 1 over x, or simply x to the negative 1. F double prime is negative 1, x to the negative 2. The third derivative, I'm just trying to get a bunch of these in here so I can try to spot a pattern. Once I put this stuff into my my Taylor series expansion. So notice that I'm not actually multiplying all of the numbers out because I'm trying to figure out what the pattern is. Because when you're trying to look at the, when you're trying to find the interval of convergence, when you're trying to see where this Taylor series is valid for, or which x values it's valid for rather, you are going to typically use the ratio test. And the ratio test is typically used with factorials. So if I can spot factorials in their wild habitat, then I can write a formula easier. All right, so okay, so those are my fifth derivatives, and it's going to keep going on like this. Now let's go ahead and plug my my center, which is x equals 1, into all of these functions. Well, f of 1 is just 0, ln of 1. F prime of 1 is 1. F double prime of 1 equals negative 1. F triple prime of 1 equals 2. And f to the fourth of 1 is equal to negative 6. Fifth derivative is 24. Okay. All right, so now that I have all of this, I can start writing out my my Taylor series. So I have ln of x, and that's going to be, well, f of 1 is 0 plus x minus 1 minus 1 over 2 factorial x minus 1 squared plus 2 over 3 factorial x minus 1 cubed minus 6 over 4 factorial x minus 1 to the fourth, and then it keeps going on. So the idea here is to look at this and try to come up with a formula with n in it. Now, what do I have? Well, one thing that I can do is I can simplify a few of these factorials a little bit. I know that 2 factorial is simply 2 times 1, which is 2. I know that 3 factorial is 3 times 2 times 1. And those 2's cancel out, so that's just 1 over 3. So let's rewrite that. And then 6 over 4 factorial. Well, 4 factorial is 4 times 3 times 2, and those 6's cancel out, and I'm left with 1 over 4. So let's rewrite that. Okay. So, can we write this in terms of n? Can we write this in terms of n? I think we can, because notice that in each of these terms, so in this term we have x minus 1 to the 1, here we have x minus 1 to the 2, x minus 1 to the 3. In other words, x minus 1 to the n, right? So this is going to be the sum as n starts at 1, goes to infinity, of x minus 1 to the n over what? Over n, right? Because this first term is over 1, we don't write it. This second term is over 2. This third term is over 3, over 4, so this is over n. Now, how do we deal with the alternating signs? Well, we bring in a negative 1 to the n plus 1. This is always going to help us with alternation, either a negative 1 to the n plus 1 or a negative 1 to the n. Why is it negative 1 to the n plus 1? Well, if we plug in n equals 1, we get negative 1 to the 1 plus 1, which is negative 1 squared, which is 1, and our first term is positive. Okay, so when n equals 1, the first term should be positive. That's gonna take care of this with this negative 1 to the n plus 1. So now that we have a formula, first of all, what did it ask for us to do? It said find the Taylor series. Well, we just did. And now I wrote all over it. And now it's not pretty, but let me rewrite this. Because there's too many circles. It's bothering me. Okay. Let me rewrite this. Okay, so hopefully you guys can see that this black series is the same thing as this, right? And you can always check yourself. When n equals 1, when I plug in 1 for every n that I see, do I get this first term? Yep, I sure do. When I plug in 2 for n, do I get this second term? Yep, sure do. And you can do it like that. So that's a way to check. There I go circling things again. Okay, now that I have this, so I know what the Taylor series is. I answered the first part of this question. This is the Taylor series. And by the way, I missed a crucial part, the plus ... That indicates that it's a Taylor series versus a Taylor polynomial, okay? Now what I want to do is I want to investigate the convergence with the ratio test. The ratio test, remember, is going to give me that interval of convergence if it does converge. Now, we did the ratio test for e to the x, the Taylor series for that, and it turned out that it converged, that series converged for any x that we plugged in. But let's check out this one. Okay, so the ratio test, well, what I have to do is first plug in n plus 1. So I have into my formula, which is right here, boxed. So when I plug in n plus 1, I get x minus 1 to the n plus 1 over n plus 1. I'm just plugging in n plus 1 anywhere I see an n. Negative 1 to the n plus 1 is n plus 2. So that's the absolute value, and that's going to be divided by just the regular formula, which is x minus 1 to the n over n is negative 1 to the n plus 1. All right, this is a mess. Let's clean it up. Negative 1 to the n plus 2 over negative 1 to the n plus 1. Well, it doesn't matter. The absolute value of negative 1 is always 1, no matter what. So basically, we can get rid of these, right? Always, no matter what n is, the absolute value of negative 1 or 1 is going to be 1. Okay? Now, for the other part, oh, and by the way, I forgot an important part, the limit as n goes to infinity. And what I can do at this point is I can take care of that complex fraction by keeping the top fraction and multiplying by the reciprocal of the bottom fraction. All right. Now, something to the n plus 1 divided by something to the n. Keep the base, subtract the exponents, and I just am left with x minus 1. So this is the limit as n goes to infinity of x minus 1 times n over n plus 1. Well, the n over n plus 1 is always going to be positive, right? Because look at where our sum started. We started at n equals 1. So I can pull that out of the absolute value bars to give me the limit as n goes to infinity of n over n plus 1. I need to leave this x minus 1 inside the absolute value bars just in case it's not positive. So here, I mean, you can use L'Hopital's rule or divide top and bottom by the highest power, but we've done a million problems like this, so I'm not going to rehash that. This is going to go to 1. So that's going to go to 1. And we're simply left with the absolute value of x minus 1. Now, the ratio test said that if this limit, which is the absolute value of x minus 1, is less than 1, then it's going to be convergent. So for what values of x is that true? Well, what we have is x minus 1 could be less than 1, or this thing in the absolute value bar could be negative. So when I add 1 to both sides, we have x is less than 2. And over here, I get, well, if I divide by negative 1, the sign needs to flip, so I get x minus 1 greater than negative 1, add 1 to both sides, and I get that x is greater than 0. Okay, so x is less than 2, x is greater than 0. So we know for sure that it's going to converge between x equals 0 and x equals 2. But remember, we need to also check the endpoints to see what's happening there. We need to check what's happening when we plug in 0 into the series and what's happening when we plug in 2 into the series. So what we know, let me see, I guess I can't go down anymore. Let me see. Well, oh well. What we know is converges. The series converges when x is greater than 0 but less than 2. But we need to check the endpoints. So we need to check 0 and 2 and make sure that it doesn't converge at one of those points. So how do we check the endpoints? Well, we look at our original series that we had, which was this guy. Or we could look at it in the above form that's boxed in black. It doesn't really matter. I'm going to erase some of this stuff. So when I say check the endpoints, I say, well, we're going to plug in x equals 0, see what happens. And then we're going to plug in x equals 2 and see what happens. Well, if I plug in x equals 0, let's write this up here, checking the endpoints. When x equals 0, I'm simply plugging 0 into this series for x. So we're going from n equals 1 to infinity of 0 minus 1 to the n over n to the negative 1 to the n plus 1. Let's clean it up. So this is going to be negative 1 to the n over n times negative 1 to the n plus 1. Well, what happens when I multiply the same base? I keep the base, negative 1, and I add the exponents, n plus 1. So let's do that. So it's going to give us 2n plus 1 over n. Okay, what is this telling us? Do we know this series? Is this a familiar series to us? Look at this exponent right here. Is this exponent ever going to be even for any value of n? Plug in n equals 1. What do we get? We get 3. Plug in n equals 2. What do we get? We get 5. Plug in n equals 3. We get 7. It's always going to be odd. Always odd. A negative number to an odd exponent is always going to be negative. And therefore, we can actually shorten this even further. We can say, hey, since this is negative 1 to an odd number all the time for every n, we can simply say it's just negative 1. That's what it's going to be, over n. Doesn't that look easier to deal with? Now this should look familiar. So if I factor out a negative 1, here, then I have negative 1 sum from n equals 1 to 1 over n, and this is the harmonic series. This is the harmonic series, and this diverges, which means that negative 1 times a divergent series is also going to diverge. And what is the bigger implication of that? X equals 0 is not included in this interval of convergence, because when x equals 0, the series diverges. It's the negative version of the harmonic series. So that's cool. So we don't put this guy under there. So let's check 2. Let's see what happens when x equals 2. So that was x equals 0. What happens when x equals 2? What happens when x equals 2? Well, let's find out. So again, I'm just plugging in 2 into my little rule right here. That gives me 2 minus 1 to the n over n to the negative 1, n plus 1, and we're summing from n equals 1 to infinity. Now 2 minus 1 is 1. 1 to the n is always 1 for any n. So we have sum of n equals 1 to infinity. This is x equals 2. 1 over n to the negative 1 to the n plus 1. Now this is something called the alternating harmonic series. Now this, I believe we've talked about it, possibly, but this thing, it actually turns out that this thing converges. It doesn't diverge like the regular harmonic series. And we can prove this to ourselves by using the alternating series test. Remember this guy? And what this guy told us was the following. It said that if I have the following conditions, if I have that a sub n plus 1 is between a sub n and 0 for all n, and also that the limit as n goes to infinity of a sub n equals 0, then the series converges. That's what that alternating series test was. So remember, our a sub n is just 1 over n without the alternating part. That's what a sub n is. So is it true is it true that, well, a sub n plus 1 is just 1 over n plus 1. We're just plugging in n plus 1 into our rule, ignoring the alternating part. Is it true that this is between 0 and 1 over n? Is this guy always going to be less than this guy and bigger than 0? Yeah, that's definitely true. For sure. What about the second condition? Is the limit as n goes to infinity of a sub n equals 0? Well, yeah, that's true too, because the limit as n goes to infinity of 1 over n, which is a sub n, when n gets huge, this thing goes to 0. So that's also true. So since both of these conditions are met, the series converges for x equals 2, and therefore we include it in our interval of convergence by giving it a little line right here. So this right here is our final answer. This is where I'm repeating myself. I don't know why. It's late. This is where the Taylor series converges. These are the x values. And x can definitely include 2, but it cannot include 0 because we saw when we plug 0 into our Taylor series, we actually got the harmonic series, the negative version, which diverges. Let's try this next example. Let's try to find the Taylor series for ln of 1 plus x about x equals 0 and investigate the convergence. So, first thing I want to do is I want to establish a pattern with the derivatives. So the first thing I'm going to do is write my f of x. That's ln of 1 plus x. And then look at my first derivative, which is going to be, well, 1 over 1 plus x, which is the same thing as 1 plus x to the negative 1. Looking at the second derivative, I have negative 1 to the 1 plus x to the negative 2. Third derivative, again, I'm not multiplying things out because I want to see if there's a factorial, involved with my formula. So this is going to be negative 1 times negative 2 to the 1 plus x to the negative 3. Fourth derivative, well, negative 1 times negative 2 times negative 3 times 1 plus x to the negative 4. And it keeps going in that pattern. Now let's evaluate at my center, which is 0, which was given to be 0. F of 0 is ln of 1, which is 0. F prime of 0 is 1, plugging in 1 into the first derivative. F double prime of 0, plugging in 0 into the second derivative function, I get negative 1. And in the third derivative, I get 2. And in the fourth derivative, I get negative 6. Now let's take a look at what this looks like in Taylor series form. So the Taylor series again, we want to see what values of x is valid for this equation that I'm writing here. So when I do the Taylor series expansion, what I get is x minus x squared over 2 factorial plus 2x cubed over 3 factorial minus 6x to the 4 over 4 factorial, and it continues in that manner. Now we have something, you should recognize this from the previous problem. Yeah, so look, how does this compare? How does this compare with our previous problem? Well, again, with these factorials, 2 factorial is just 2. 3 factorial is 3 times 2, so 2 over 3 factorial is just 1 over 3. And then 6 over 4 factorial again is just, sorry, I'm losing it here. So 4 factorial is 4 times 3 times 2 times 1. And so again, the 3 times 2 is going to cancel on numerator and denominator. And I'm just left with 1 over 4. Perfect. So that is my Taylor series expansion. Now, we want to figure out which values of x is this equation a valid equation for, right? Because for x values that aren't in our interval of convergence, it's not going to be valid. So we need to figure out the interval of convergences. But before I do that, I want to write this Taylor series in terms of n so that I can use my good old ratio test. So what do I have here? Well, I have a sum, and I'm starting at n equals 1, and I'm going to infinity, and I have x to the n over n, and my signs alternate. So to account for that, I'm going to tack on a negative 1 to the n plus 1. Does this work? Well, I think it does. If we plug in 2 anywhere we see an n, we do indeed get this. If we plug in 3 anywhere we see an n, we do indeed get this. If we plug a 4 in our formula for anywhere we see an n, we get this. So this guy is our a sub n formula, okay? Now let's go ahead and use the ratio test. So the ratio test, I need to take the limit as n goes to infinity of the absolute value of a sub n plus 1, so that's going to be x to the n plus 1 over n plus 1 to the negative 1 to the n plus 2. Okay, so that's going to be multiplied by the reciprocal of a sub n, which is n over x to the n, to the negative 1 n plus 1. Okay, so again, these negative 1s can go away. Remember, we're just taking the absolute value here. And the x to the n plus 1 divided by x to the n, keep the base x, subtract the exponents, and we end up getting simply x. So the limit as n goes to infinity of the absolute value of x times n over n plus 1. That's what we have. Now again, same deal as before. We can bring the absolute value of x in the front. We're taking the limit as n goes to infinity of n over n plus 1, and we know that to be equal to 1. So this is 1, and so therefore we have the absolute value of x. Now the ratio test tells us that if this limit, which is the absolute value of x, is less than 1, it converges. So for which values of x is that valid for? Well, it's going to be valid for x is between 1 and negative 1. So now we need to check the endpoints. We need to be careful and check the endpoints here. So what happens if I plug in negative 1 into this series? So let's check our endpoints. So when x is equal to negative 1, I'm plugging that in here. I get negative 1 to the n over n times negative 1 to the n plus 1. Well, I can clean this up by multiplying these negative 1 to the n and the negative 1 to the n plus 1. And I do that by keeping the negative 1 and adding the exponents. So this becomes negative 1 to the 2n plus 1 again. Does this look familiar? So we're going from n equals 1 to infinity. And this is always odd. Okay, so that means that this thing, again, just like before, I hope that you see what's going on here. This is just going to be negative 1 on top, right? Because this is always odd. So again, we just talked about this. This is going to diverge. This is the negative version of the harmonic series, and therefore negative 1 is not included in our endpoint. However, let's check 1. Let's check x equals 1. If I check x equals 1, just plugging 1 in here, 1 to the n over n to the negative 1 to n plus 1. 1 in the n is always 1, so this is 1 over n. And we just did this problem. This is the alternating harmonic series, and this converges by the last problem. So we are going to include 1 in our endpoint. So this is where the function converges. And yeah, so that was that. Let's do some other examples of using the Taylor series. So we can do some clever tricks in finding and using Taylor series. And the first trick that we're going to talk about is talking about new series by substitutions. So the question is, how can we find the Taylor series for f of x equals e to the negative x squared? What does this mean? Well, what I can do is I can just look at the basic function of e to the x, but instead of e to the x, I'm going to make a substitution here. I'm going to say, well, how about we let y equal negative x squared, right? So then this is going to equal e to the y. Well, e to the y, we know what that is. We just have 1 plus y squared over 2 factorial plus y cubed over 3 factorial, and so forth and so forth. Y to the 4 over 4 factorial, and it keeps going. So all we have to do at this point is substitute in anywhere we see a y, negative x squared. Isn't that clever? So therefore, e to the negative x squared is going to equal 1 minus x squared plus, well, what's negative x squared? That's going to be a positive x to the 4 over 2 factorial. And then we just continue plugging in negative x squared in for y and simplifying. So that's a little trick here. Pretty sneaky. So that is going to be the Taylor series for e to the negative x squared right there. Let's do another example. So here we have f of x equals 1 over 1 plus x squared. So we talked about 4 different special types of Taylor expansions. We talked about e to the x, we talked about sine of x, we talked about cosine of x, and then we talked about that binomial 1 plus x to the p. Which of those does this most resemble? Well, I'm thinking that it resembles the 1 plus x to the p the most. And here's the substitution we're going to make. We're going to let y equal x squared. And when we do that, this is going to equal 1 over 1 plus y. Now, writing this as a power, we have 1 plus y to the negative 1. Aha! Now we have 1 plus a variable to p being negative 1. So we want to use our 1 plus x to the p formula centered at x equals 0. And when we do that, we get this. We get 1 over 1 plus y, which is equal to 1 plus y to the negative 1, which is our p, equals 1 minus y plus y squared minus y cubed plus y to the 4th. I'm not showing all my work here, but just know that I'm plugging in p equals 1 into the equation, the Taylor series for 1 plus x to the p, except instead of x, I have y. Okay? So there it is. And so my last step is to sub back in x squared for y. And so what I have is 1 over 1 plus x squared is equal to 1 minus x squared plus x to the 4th minus x to the 6th plus x to the 8th and so forth. So this is my expanded series right there. Okay, so here's the next example I want to look at. So we can also find new series by differentiation and integration. So we want to find the series about, or find the Taylor series about x equals 0 for 1 over 1 minus x squared from the series for 1 over 1 minus x. Now we know what the Taylor series for 1 over 1 minus x is. So 1 over 1 minus x is going to equal 1 plus x x squared plus x to the third plus x to the fourth plus dot dot dot, where -1, so x is between -1 and 1. So this is just our geometric series with a common ratio of x. Okay, so this is the observation we want to make. It turns out that the derivative of 1 over 1 minus x, well, that's just equal to 1 minus, 1 over 1 minus x is the same thing as 1 minus x to the -1. And so the derivative of this guy is just going to be, well, it's just going to be -1 times 1 minus x to the -2 times the derivative of the inside, which is -1, and those negative ones make a positive. And notice that this guy is 1 over 1 minus x squared, right? So the derivative of 1 over 1 minus x is equal to this guy. So what I'm going to do is I'm just going to take the derivative of all of these terms, and that's going to give me the Taylor series for 1 over 1 minus x squared. So let's go ahead and do that. So 1 over 1 minus x, well, let's write it like this. d dx of 1 over 1 minus x. Okay, so if I differentiate term by term, I just get 1 plus 2x plus 3x squared plus 4x cubed plus dot dot dot. Again, this is going to be our Taylor series, and this is the derivative of 1 over 1 minus x. The derivative of its Taylor series is going to be the Taylor series for 1 over 1 minus x squared. So this right here is going to be our Taylor series expansion. All right, find the Taylor series about x equals 0 for tan inverse x from the series 1 over 1 plus x squared. So the first observation we can make is when we take the derivative of tan inverse of x, we get 1 over 1 plus x squared. That was one of our special derivatives that we learned last semester. So we actually just did this problem. So this was a few slides ago, 1 over 1 plus x squared, this guy. So we already found the Taylor series for that. So let's go ahead and write it out. All right, so there's our Taylor series for that guy. And what I need to do now, well, it turns out that since the derivative of tan inverse of x is 1 over 1 plus x squared, the integral of 1 over 1 plus x squared is going to equal tan inverse of x, right? And so all we have to do is integrate this guy. Once we integrate that guy, we'll have the Taylor series for tan inverse of x. So let's integrate it. So antiderivative of 1 is x. Antiderivative of minus x squared is minus x to the 3 over 3, and so forth. Okay, so this is going to be our Taylor series for tan inverse of x. All right, let's do some more clever tips and tricks. So find the Taylor series for x squared sine of x about x equals 0. How do we do it? Well, it's not so hard. We know that the Taylor series for sine of x is going to be x minus x to the 3 over 3 factorial, centered at 0, by the way, plus x to the 5th over 5 factorial minus x to the 7 over 7 factorial plus dot dot dot. And all we need to do is simply multiply x squared on both sides. So we need to multiply this whole thing by x squared, and we need to multiply sine of x by x squared. And that's going to give us what we want. So when I distribute this x squared in there for all of those guys, I get the following. I get x squared sine of x is equal to x to the 3 minus x to the 5 over 3 factorial plus x to the 7 over 5 factorial minus x to the 9 over 7 factorial, and so forth. So this is going to be my Taylor series for x squared sine of x. All right, let's do another one. So it says, find the Taylor series about x equals 0 for sine of x, cosine of x. So we want to make a little observation here. And the observation is that we have a trig identity. The trig identity is the following. It's called the double angle formula. Well, no. Is it called the double angle formula? Anyway, okay, it's this identity. It's 2 cosine sine of x, or maybe we'll write it like it is here, sine of x cosine of x is equal to sine of 2x, double angle. So if I want to see what I have here, I just divide both sides by 2 to isolate the sine cosine, and my identity becomes sine of x cosine of x is the same thing as sine of 2x over 2. So all we have to do is, instead of plugging in x into my sine of x expansion, I just need to plug in 2x and then multiply by a half. So maybe we'll start with sine of 2x first. So this is equal to this, and so the sine of 2x, I'm just plugging in 2x into my sine expansion. So that's going to be 2x minus 2x to the third over 3 factorial plus 2x to the 5th over 5 factorial minus 2x to the 7 over 7 factorial plus 2x to the 9 over 9 factorial, and our pattern continues. So that's sine of 2x. Now what about sine of 2x divided by 2? Well, we just divide everything by 2. So 2x divided by 2 is x. This guy, the second guy, divided by 2. Well, that's just going to be, I'm going to be lazy and not really simplify anything. That's just 2 times 3 factorial plus 2x to the 5th over 2 times 5 factorial, and so forth. And the pattern continues. And remember, this is equal to sine of x cosine of x. We have a trig identity that tells us that. So this guy is going to be my Taylor series expansion for this guy. Let's do one more example. Find the Taylor series about theta equals 0 for g of theta equals e to the sine theta. So how are we going to deal with this? Well, the first observation we can make is that we can do a substitution. We can say, okay, well, let's let y equal sine of theta, or x, or whatever variable you want. And so our Taylor expansion for e to the y is going to be 1 plus y squared over 2 factorial plus y to the third over 3 factorial, and so forth and so forth. And so, what we have here, once we plug our sine of theta in for y, we have e to the sine theta is going to be 1 plus sine theta plus sine squared theta over 2 factorial plus sine to the 3 theta over 3 factorial, and so forth and so forth. Now, if we wanted to get everything just in terms of theta, which is usually a good idea, we can further simplify this because we know what sine of theta is, what the Taylor series for sine of theta is. Let's just rewrite this. Actually, no therefore, just a note. Sine of theta, instead of x, we're using theta, is theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial. So now all we have to do is plug in this stuff anywhere, anytime we see a sine. Okay? So here we go. Let's do it. Therefore, e to the sine theta is going to equal 1 plus, okay, now I'm doing the substitution. Theta minus theta to the 3 over 3 factorial plus theta 5 over 5 factorial. And I'm just going to leave it at that. So there's my first sine theta. Then I have sine squared theta. So I have 1 over 2 factorial times sine squared theta. So that's just theta, again, minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus ... And it's going to continue in this pattern here. The next one would be 1 over 3 factorial theta minus theta cubed over 3 factorial plus theta to the 5 over 5 factorial minus ... to the 3rd power. And it's going to continue in this fashion. And yeah, so if you want, you can group things together and things are going to cancel out quite nicely. So maybe I'll leave that as an exercise for you guys. So exercise. The exercise is going to be to condense the above Taylor series. See if you can rearrange the terms and clean it up a little bit. But for now, I'm just going to leave it expanded as it is. So try that out, and that is going to be our last problem of this lecture. So thank you very much for watching. I really appreciate it. I'll see you guys in the next video.